So first of all, thank you to Kai for organizing this session and just in general these sessions on UHPC every year. So today what I'll be talking about is the seismic behavior of structural systems with highly ductile concrete materials. And the first thing I'd like to just kind of point out is just the overall mechanical behavior of these types of materials. So we focused on UHPC in this presentation. One of the unique advantages of UHPC is that it has a very high tensile strength in addition to its compressive properties, and it has these high strain capacity as well. And the focus of my presentation will be on both UHPC, but other types of materials as well that have these strain hardening or pseudoplastic type behavior. And so these are just commonly referred to in the literature as HPFRCC type materials. And so I'll be using both UHPC and HPFRCCs just generally throughout the presentation. Within the seismic community, these materials have been investigated significantly over the last 2 decades. So one example here is in coupling beams, which link together adjacent shear walls. And so the idea in this study from about a decade ago was using these types of materials to reduce reinforcement congestion in these types of elements. So they're significantly costly to construct from a labor standpoint, but in addition, rebar tonnage as well. And one of the unique aspects of these types of materials is that they have very excellent performance from a damage perspective. So we don't get the same level of concrete spalling or significant cracking that you see in a reinforced concrete structure. So what I'd like to do is just take a step back and think about sort of the use of these types of materials, specifically UHPC. And in UHPC, one of the nice things that the Federal Highway Administration has done is if you go on their website, you can see all the applications that UHPC or a number of applications that UHPC has been documented across the United States in bridge infrastructure systems. And UHPC has grown substantially in the bridge construction industry. So just pulling the data off of the Federal Highways website, you can see the rather significant growth that UHPC and similar types of materials have gone through over the last, especially decade, in terms of cumulative number of applications of these things. But we haven't seen the same level of adoption in the seismic design space. And so what I'd like to do is just talk about some of the challenges that exist in that space and some opportunities that we have to better understand how to design buildings with these materials for seismic design. So these systems have been investigated in a number of different applications, mostly in regions where you would need to dissipate damage that may occur within a building frame. So in plastic hinge regions, this is where we would expect lots of damage to occur in beams and columns. In areas where there's high shear and bending, they've been investigated heavily. In locations to reduce transverse reinforcement requirements or operate as structural fuses. All of these are potential applications for these types of materials. So one of the unique aspects from a seismic design perspective is how differently these members behave when you load them from initial loading to failure. So this is representative load displacement plot. And generally speaking, UHPC type of system will have a higher cracking load, first cracking load, and from a structural perspective. Like reinforced concrete, the steel eventually yields. The main difference is how they fail. So a reinforced concrete member will generally fail due to crushing when it's loaded in flexure. But the UHPC and other types of materials that are like it, they won't crush. Instead, what will eventually happen is that there will be a loss of that tensile capacity, and that's then transmitted to the longitudinal reinforcing bars. And very often, after crushing in a reinforced concrete member, you return to the behavior of just the steel cage, whereas with a UHPC type system, you can either eventually get to the reinforcing bar fracturing or a localization and fiber pullout. Now, one way to look at this is that with a UHPC type system, you're really engaging all of the materials that are in your structural component and able to fully account for this. But how we have to think about it from a seismic design perspective is how do we design for these different failure modes? So this is data from large-scale physical experiments tested out to failure. So oftentimes when we do structural tests, we stop, kind of a little bit after yield or whatever it might be. But these are all tested to a failure point. And on the x-axis are different types of failure modes, and on the y-axis is basically a measure of deformation. So it's the deformation divided by the shear span length in this plot. But what you see is that almost all of the specimens that are tested out to these very high levels of deformation aren't failing due to crushing of the material or buckling of the bars or shear. They're failing due to loss on the tension side of a flexural element, right? So and that might be fracture of the bars or fiber pullouts. And where this relates in seismic system analysis is, so a structural engineer, if they were to design and analyze a system, what they do is they build computational models like this. And these computational models consist of plastic hinge regions, locations where we would expect damage to occur within panel zones, these sorts of things. But basically, elements are modeled using lumped plasticity types approaches. So that might be a fixed length hinge model or a spring hinge model, where basically you're characterizing the behavior down to just kind of moment versus rotation. And so it's kind of simplified, but we need to, in order to use these types of materials in seismic design, we need ways to predict this sort of behavior. How do you predict moment versus rotation when you have a very different failure mechanism, when you have very different deformation capacities, all these sorts of things. And so what we've done over the last few years is look into how do existing models work with these new types of materials. And it turns out basically the traditional way we calculate rotational capacities don't work with UHPC type systems. And so here are examples. So these are sort of widely used expressions to figure out rotational capacities of elements. And instead of rotational capacity, you can just think of displacement capacity or deformation capacity. And so on the x-axis are experimental values, and on the y-axis are ways that we would use today for reinforced concrete to predict the rotational capacity. What you see is that basically the experiments and the literature that's used for reinforced concrete don't line up at all. So the one-to-one line is that diagonal line there. And you can see all the stuff that we would use for reinforced concrete can't work for the experiments. And so these are monotonic cyclic experiments for a wide range of strain hardening type of fiber reinforced concretes, including UHPC. So what that means is that we need to account for failure modes, ductility, distribution of damage when we're using UHPC and similar systems. So can we go through the process and say, okay, how did we do this for reinforced concrete? And let's just repeat it again for these new materials. So for reinforced concrete, basically what's been done over, in the 20th century and the early 21st century is basically, we execute a series of experiments and we repeat those experiments across a range of variables. So maybe we're changing how much reinforcement is in there, or span to depth ratio, or compressive properties, whatever it might be. And then we fit some sort of model to that. Now, the challenge for doing this with UHPC is, one, there's a limited set of experiments that are kind of out there, right? It's a newer material. The material is changing fast. And we have a limited experimental database to kind of pull from. Two, it takes time to create those large-scale experiments, right? And three, as we've seen throughout the day today, there's constantly new innovations, whether it be through kind of re-engineering the material with carbon nanofibers, or new types of material constituents that go in the system. So an alternative approach that we've taken is to rely on computational models to help us build a database of experiments. And when I say experiments, I'm talking about experiments that our computers run. So what we might do is begin by executing simulations, right? So Kai earlier talked about using sort of some new material models to predict behavior. So maybe we take those models and build them into a structural simulation, and we could repeat those across the same set of variables. So we could repeat it with, different amounts of reinforcement or span to depth ratio or tensile properties, compressive properties, whatever it may be, and then fit a model to it. And the key here is, nothing in this line so far has mentioned anything about physical experiments. Now, if I did this and, I stopped there, you would say, well, the model is just fitted to a computer model. So what's the, how do I trust that? So it turns out our computer models are actually very good. And so we've gone through this approach, and we've been able to show that if you don't do anything in the first few steps with experiments, and then you go and you validate it with a set of experiments, it works very well. So these are actual experimental data points on the x-axis, and then on the y-axis is what we would predict going through these 3 steps. And you can see, unlike when I showed the reinforced concrete where all the data points were up here in the top left, now when I've gone through the process and built things from the computer models and then verified it with the smaller, albeit smaller set of experiments that we have, but we do have several dozen large-scale experiments, it works much better than what we might use for reinforced concrete. So now that we have some initial ways of predicting rotational capacity, how can we go through the process of seismic component analysis and design? So the way that this works, once again, is we basically try to lump all of the damage that may occur into a nonlinear spring at the ends where we would expect damage to occur in an earthquake application. So we build those nonlinear springs, we develop some sort of rotational model that accounts for the backbone and cyclic behavior, and we try to meet some target objectives. So predicting strength, predicting how much loss happens within a cycle, predicting the deformation capacity. And we're able to do that quite well. So we can compare the numerical and physical experiments. And so now we have these lumped plasticity type models, which are what structural engineers actually use if they were to go through a performance-based earthquake engineering approach to design with these types of materials. So what I'd like to do is illustrate an example that we've done with this. And so this case is, so first we went through and used a widely used kind of code-conforming reinforced concrete structure that's been evaluated in the literature. And so this is designed using code practices from today. And then what we did is we repeated this, and all we did is in the beam regions, the beam plastic hinge regions, we replaced the reinforced concrete with a material like UHPC. And so no other changes were made, just replacing material for material. We haven't downsized section sizes or anything like that, just material for material. If you're a structural engineer in this space, you may say, why didn't you change the columns? And the correct answer is we should be. But the problem is that there's even less experimental data with columns. And so this first approach, we're just doing it in beam regions. And then this second case, what we did is we redesigned it another time, but basically we've accounted for the fact that, okay, we are going to get more strength, and by having more strength, I can decrease section sizes. So for example, here you see a 76 centimeter by 76 centimeter member, and here you see a 76 by 66 centimeter member. So you can, just to illustrate, okay, what happens as I begin to actually really account for all of the enhanced mechanical properties and material properties with this. And so basically the steps for this, first what we do is we develop that system model. So we take kind of the actual structure, we model it numerically in the frame kind of sticks that you see there with all the lumped plasticity, and we fit the backbones. And then we subject it to a series of earthquakes. So what we're using in this example, if you're familiar with it, is an incremental dynamic analysis approach. But basically what it means is I take an earthquake record and I shake the computer model to that earthquake record. And then I take that same earthquake record and I shake it to a higher intensity. And I keep doing that until the structure collapses. And that tells me, what's the collapse capacity of these structures. And I do that across different types of earthquakes. So maybe something from the 1989 Loma Prieta earthquake versus the 2011 Tohoku earthquake in Japan. And then what I'm able to do is look at, for varying amounts of earthquake intensity, what's the corresponding deformation that happens in the system, right? So we look at this in terms of inner-story drift ratio, but on the y-axis, basically, you're looking at earthquake intensity versus how much damage occurs. And eventually, you can imagine as I scale up the intensity, the structure just collapses, right? And it can't take anymore, so the deformation just sort of falls over, and that's what you're seeing in this case. So these are plots of these three structures: the reinforced concrete frame, the first frame that didn't account for the enhancements in the material, and the third frame is when you do account for the enhancements of the material. And I'll just explain what this data represents. So each of those gray lines represents a single earthquake that's been scaled up to 1 times the record or 1.5 times the record or whatever it might be. And the red line represents the median response. And again, the y-axis represents earthquake intensity, and the x-axis represents the system deformation. And when you look at them kind of side by side, it's difficult to exactly interpolate what's happening. So let me highlight a few key points. So what you see here is, first, when the increase in moment capacity of these HPFRCC or UHPC type systems was not accounted for, the system was more likely to collapse, almost by 50%. You would say, well, why would anyone use this type of material in seismic design if that's the case? And the reason is that when you do re-engineer it, when you do account for the added strength you get with these types of materials, I've suddenly reduced the probability of collapse under the maximum considered earthquake by almost 40%. And this has to deal with the fact that in this example we used the materials just in the beam regions, and you have to maintain a strong column, weak beam. But the interesting thing here is that basically we just have to re-engineer or go through our structural design process and really account for the advantages that you get with these materials. And now I have a 40% less likelihood of collapse under the largest earthquake that we can sort of simulate. So some of the limitations of the work to date, we've just got limited experimental data on members with axial load, and that's why that first frame didn't have them in the columns, it just had it in the beam regions. Other limitations, the system level analysis of structures with materials and components beyond beams, so in like those shear link beams, those sorts of things. There's other variables to consider. How effective are they across story heights or different lateral resisting systems? There's UHPC systems that are out today, but that's going to change in a few years, right? How do we consider that? And what's the overall cost effectiveness when you look at it from a seismic design perspective? So we recently started a project, and it's in the first year of a 5-year, but basically there's a few different objectives that I'll highlight. The first is to investigate elements under combined load effects. So here what we're going to be doing is physical experiments and numerical simulations with different amounts of axial load and lateral loading to try to be able to predict these systems or the behavior of systems with in column elements. We'll then be developing these plastic hinge and rotational capacity functions, integrating some of that data. We'll be assessing the structural response across various frame heights and story configurations, and then looking at what are the life cycle costs of these systems, how much potential advantages do you have from material usage, et cetera. And so we are right here. This project started August 1st, so we're right at the beginning of this second portion of the work. So let me point out a few things that we've done. So we have some experiments that'll be coming up in the laboratory later this year, but we've been using numerical tools to investigate the effects of axial load, much like we've previously done them before, without axial loading. So what I'll show you in a second is basically plots of moment versus drift or moment versus rotation with different amounts of axial load. So ALR is the axial load ratio. So 0% would basically just be a beam, no axial load applied to it. 5% would be basically you're applying a compression force that's equal to 5% of the column's compression capacity. 10% would be 10% of the column's compression capacity, et cetera. And this is kind of what we see. And the unique thing here that's occurring is as I increase the amount of axial load up to a certain point, I'm getting more displacement capacity. That's unique. So in a reinforced concrete member, traditional reinforced concrete, as I apply axial load, because the members fail due to loss of compression capacity, I would reduce, you'd see sort of the opposite behavior. So what this shows is sort of the promising aspects that these materials have in column applications for seismic design. Now that kind of switches at some point. So an applied load ratio of 15%, it begins to move back towards, and you begin to lose some of that ductility. But basically what's happening is the axial load is relieving those tensile strains in the reinforcement in the HPFRC or UHPC system, and that can result in an increase in deformation capacity. Just to point this out, so this is data from for reinforced concrete members, and basically what it's showing is as I increase the axial load, my rotation capacity goes down using ASCE 41, using and what's kind of out in the literature. But basically, as I increase the amount of axial load, I shift this graph to the left, which means I have less displacement capacity or less load or less rotation capacity. And so that's what we would note for reinforced concrete. And these are from numerical results. What we see for this in this example, it's UHPC. So what I'm basically looking at is if I look at a particular reinforcement ratio, as I increase the axial load, the colors are getting lighter, and that means that it's getting more rotational capacity. So these contours represent rotational capacity. And what that tells us is, once again, this behaves kind of very different than what we'd expect reinforced concrete. So in summary, UHPC and other systems with high ductility have these unique failure modes, and that necessitates a sort of new models in seismic analysis and design. There's significant potential to improve life safety and reduce damage. So, if you can take away one thing, it's that example that showed that we could reduce the probability of collapse by 40% by using these types of materials. And there's new ongoing work to understand the broader set of seismic design systems with UHPC and similar systems. And with that, I thank you and happy to answer any questions.